double theories. Go ahead, Evan.
Hey, thanks, Kevin. Yeah, so this is a project that's been in the works for a long time. The premise, as the subtitle here suggests, is to use ideas from double categories to give an account of doctrines. And if you don't know what a doctrine is, that's okay. I'm going to tell you. Yeah, so this is joint work with Michael Lambert. Some of you have heard preliminary versions of this talk, in which case bear with me because I'm going to start from the beginning. And the paper that we've written about this is basically written. We're in the process of editing it, and it should be out in the archive within the next week or two. So at this point, I'm reporting on work that's essentially done. Okay, so the story of categorical logic, which is going to be sort of our starting point and motivation for this work, originates with Leverre's thesis, Functorial Semantics of Algebraic Theories, which told the following story. And the idea is that one can identify with an algebraic theory a certain kind of category, namely a category that has finite products, and then product-preserving functors out of that category into set correspond to models of the algebraic theory. And finally, if we look at natural transformations between those correspond to homomorphisms between the models of the theory, and one can go really far with this and draw out some really interesting dualities between syntax and semantics. And the picture that this presents is that the study of logic from the categorical perspective is intrinsically two-dimensional, because we can see that all the levels of the two category of categories are present here, right? We have categories, functors, and natural transformations. They all play a crucial role. From this starting point of Cartesian categories and algebraic theories, one can explore a whole sort of hierarchy of notions of theory or logic that sit below or above or adjacent to, in some way, algebraic theories. So this is not the conventional hierarchy from categorical logic. I'll come to that in a moment. But a lot of the activity that's gone on in applied category theory has been about exploring what might be called the monoidal hierarchy, so looking at notions of theories that are in some ways actually weaker than Cartesian categories. Maybe you're just looking at a symmetric monoidal category. It might have some extra structure. And the sort of theory that one can look at, so monoidal categories are often used to describe theories of processes of some kind. They could be classical processes, quantum processes, and depending on what kind of thing you're looking at, you might add different gadgets to it. And then, if you're familiar with categorical logic, you might be thinking more about this sort of thing. So starting from this correspondence between Cartesian categories and algebraic theories, there was a whole research program that has gone on for many decades of building up from that, a whole hierarchy of different connections between notions of category with extra structure and different notions of logical theories. So I won't go through all of these. Some of the quite significant ones are the correspondence between Cartesian closed categories and the typed lambda calculus with product types. And at the top of this hierarchy, usually people would consider that to be an elementary topos, which encompasses a very expressive kind of higher order logic. Okay, and this picture of logic has some, I think, quite significant implications. I mean, first of all, it suggests that rather than mathematics being something that reduces to logic, and logic sits at the bottom, in fact, logic is a part of mathematics. It corresponds to different kinds of categorical structures, and we study them as mathematical structures in a way that's perfectly analogous to how we study other kinds of algebraic gadgets in mathematics. And it also suggests that rather than logic being about searching for one true foundation, that foundations are pluralistic, and that depending on the sort of scenario in which one is modeling, you can choose, or in some cases even construct, out of different categorical gadgets, a logic that's suitable for the task at hand. And I think this is a really powerful and beautiful picture, and it's motivated a lot of my thinking about category theory and applied category theory over the years. But if you're a category theorist and you're looking at this, you got to ask yourself, okay, we like to organize things, we like to taxonomize things in category theory. How do all these different logics fit together? And it appears at minimum that a logic is described by a two category. And if we look back at these pictures, these arrows are some kind of forgetful functors between two categories, but we'd sort of like to systematize this somehow. And this is where the notion of a doctrine comes in. So this funny word doctrine in this context means something like a categorification of a theory. So, you know, in logic, we think of a theory as specifying a set or maybe a family of sets that are equipped with some extra structure. You know, these include a lot of the familiar things from abstract algebra, like groups and rings and monoids and all that fun stuff. Categorifying a doctrine is supposed to specify a category or maybe some family of categories that have extra structure. And so intuitively, that's what a doctrine is, but we want to be more precise. It would be better to have a more precise account of what a doctrine is. And so the word doctrine, like the word theory, is not on its own a precise term. It's sort of an idea. And there are different ways of making it precise. And my own interest in this topic arises from a situation where one has no choice but to be precise, which is where, if you're doing computational category theory and you want to be looking at different kinds of categories or categorical logics, you are forced to have some sort of unifying way to describe them. So that's one of the things that has been pushing me towards this topic for a long time. So a place where I'll take as a point of departure are generalized algebraic theories, because a number of us here have worked on that quite a bit. So, and the motivation for considering these is that pretty much any kind of categorical or higher categorical structure that is purely algebraic, meaning it's defined solely in terms of algebraic operations, not, say, with reference to universal properties, is a model of a GAT. So GATs were introduced by Cartmill, and one can think of them as being the minimal extension of algebraic theories with dependent types. And they have the same expressivity as some other things you might have heard of, such as finite limit theories, or essentially algebraic theories. Kevin had a nice talk in a seminar recently explaining a bit about these, how these connections work. And in our computational work, first in CatLab and now in this new project, GATLab, being developed mainly by Owen Lynch and Chris Brown, we've really sort of explicated this as a computational structuring device for applied category theory. So GATs are great. There's a lot to like about them. But one thing that they're not is that they're not doctrines. And the reason that they're not doctrines is that a GAT in general has a one category of models. And I don't know of any way of extracting from an arbitrary GAT any kind of higher dimensional structure. And I'm pretty doubtful that you could, because in as far as GATs include not just categories, but two categories and double categories and all sorts of higher structures, it's very hard to imagine that one could get all of that structure all those higher structures for free out of that. Okay, and so we may not know what a doctrine is, but one thing that's pretty clear is that if you're going to have that a doctrine needs to give at least a two category of its models. Okay, and so the standard answer to what is a doctrine is that a doctrine is a two-monad on cat. And this slide's just for background, so if what I'm saying here doesn't make any sense, that's okay, because we're not going to talk about it again after this. But the idea here is that you can have particular two monads on cat whose algebras include a lot of the things that you might be familiar with, like symmetric monodal categories, or categories with finite products or finite limits. there's a notion of strict pseudo and lax morphisms between these algebras that recover what you would expect. So like strict, strong, lax monodal functors and stuff like that. In between those, there's a notion of transformations, which gives a two-category of algebras. And so this is a really highly developed theory. Max Kelly, I think, did a lot of the early work on it, but it's been developed by a number of people from the Australian category school. So it's a powerful and highly developed theory. But at least to me, it seems hard to work with concretely. As far as I know, there's no simple way to present two monads by generators and relations. So there is a sense in which two monads can be presented, but it's quite a bit more technical. And in particular, I've never really had any idea how one would do computer algebra with two monads, which is not to say it's impossible, but I'm not sure what one would do. So the motivation for this talk is to say, well, can we think of a notion of doctrine that would be analogous to, or in fact categorifying, algebraic theories? So you might have heard that Lebesgue theories, which correspond to the single-sorted algebraic theories, are in a sense equivalent to finitary monads. There are several ways of making that precise. But once you're thinking about finite product theories, they have the nice advantage that they're quite easily and naturally presentable by generators and relations. It's pretty easy to give them concretely. So it's really natural to ask, how can we categorify that thing? And relatedly, what would it mean to have a notion of functorial semantics, which is the key idea in categorical logic that is suitably two-dimensional? And I'm going to start to try to get at this by going back to actually a very early observation, I think first noticed by Benabou, that a lax functor from the terminal category to the bicategory of spans is the same thing as a small category. You might have seen this before, but if not, that's okay. We're going to do this in more generality later. Actually, Benabou, I believe, was the inventor of both bicategories and lax functors, and this was motivating to him. And moreover, this observation generalizes in a number of different interesting ways. Like you can replace the terminal category or the bicategory spans with different things and get other sort of nice correspondences. And so one might think that bicategories and lax functors might be a place to start for two-dimensional functorial semantics, but one immediately hits a problem, which is that if you look at the cells between such lax functors, the ones that are well-behaved are these things called icons. And what those turn out to correspond to, if we're viewing the lax span-valued functors as categories, is functors between categories that are identities on objects, which is really very restrictive and bizarre notion to consider. So, from my point of view, this observation about bicategories, kind of can't really get off the ground due to this problem. Okay, but now we're going to see something interesting, which is that if you look at a lax functor of double categories, where we take as the domain the terminal double category, and the codomain is the double category of spans, whose arrows now include functions. Well, this is again a small category, and in fact, at this level, the functions aren't doing anything. They're just sort of there in the receiving structure. But the important thing that happens is when you look at cells between these, so there's a good notion of natural transformation between lax double functors. They're sometimes called vertical transformations, and the conventions that we'll adopt here, those correspond precisely to functors. So that's good. And surely many people have noticed this over the years. It's fairly immediate. But what we're going to see is that this observation is the beginning of a much more elaborate story that we can tell. Okay, and so the big picture that we're trying to develop in this line of work is something like this. We're interested in so-called double theory, and we're going to think that a double theory is a double category, possibly with some extra structure. So a double theory, like a theory, is at this point not a precise notion. A model of a double theory will then be a lax functor from that into span that suitably preserves this extra structure. And then what we're going to see is that the models of the double theory should be the objects of at least a two category of models. Actually, we're going to get a lot more than that. We're going to get a double category of models, and we're even going to get an equipment of models under suitable assumptions, with the caveat that sometimes these structures can be virtual. So basically what we do in this project is develop this idea in a great deal of detail for two particular kinds of double theories. So first of all, we're going to look at simple double theories where we're just looking at double categories with no extra structure. So if we're thinking that there's some kind of hierarchy of double theories, these are at the bottom. And then we're also going to look at Cartesian double theories, which are what you get when you add finite products in the double categorical sense of product. Yeah.
So you're talking about formalizing the word doctrine, so you're going to define a doctrine as a double theory.
That's right. That's right. That's where we're going. Yeah, thanks for making that clear. Okay, so to kind of drill down a little bit more into what are the concepts that are going to be involved in explicating this. So a simple double theory is going to be a small double category, which it's convenient to also take to be strict. A model of that will be a lax span-valued functor, as we've motivated a bit. A morphism of the models will be a natural transformation, which we've also gestured at. But what we're going to do here is we're going to have a way to recover not just the strict maps, but also the pseudo and the lax or the oplax ones by considering suitable notions of pseudo or lax natural transformation. We'll get a notion of bimodule or generalized profunctor between modules, which corresponds to a known notion known as a module. And finally, we'll get a two-dimensional cell between two morphisms and two bimodules, and that thing turns out to be something that's called a modulation. So these notions of modules and modulations for lax double functors were introduced by Bob Perret in, I think, some quite significant papers. So in terms of these mathematical structures, the main thing that seems to be new here is that we've considered generalizing these natural transformations between lax double functors to also possibly be lax themselves. So I'll discuss that a bit. In the Cartesian case, okay, the glib way of saying this is that we just start slapping Cartesian in front of everything. But what are we saying here? So in this talk, the word Cartesian always means that we either have or preserve finite products. So a Cartesian double theory is going to be a small strict double category that has finite double categorical products. A model of those will be a lax functor that preserves those products, and similarly for the higher cells. Cartesian double categories have been studied in Eva Eleferi's thesis, which was not about 5 years old now. The notion of Cartesian in there is compatible with the general notion of limits in double categories that goes back to the theory by Grandis and Perret. And the notions of Cartesian transformations and Cartesian modules are notions that we, as far as I know, introduce in this work. Okay, so all of that was sort of by way of extended introduction, and now I'm going to start to get into some of the meat of this stuff. Any quick questions before going on? Yeah. Okay, one other point I wanted to make actually about this is that, as you may have noticed, a lot of the structures that we're using here, most of this stuff is already out there. So to me, there's something kind of remarkable about the fact that these concepts from double categories weren't invented to do this. They seem to want to do this on their own, and to me, this is a a pretty good argument in favor of the use of double categories for a kind of categorified logic. Okay, so now I'm going to talk a bit about lax functors between double categories and then look at some examples and definitions and results concerning simple and Cartesian double theories. So first, some preliminaries. So if you haven't seen double categories before, I'm sorry, it's not going to be sufficient. But what I'm doing in this slide is basically just sort of setting sort of notation and terminology. So the way we think of double categories is that they're a category, or to be more precise, a pseudo-category in cat. And so what we have in one of these is a category of objects and arrows, which we denote D0, and a category of proarrows and cells, which we denote D1. And then there are two functors from D1 to D0, giving sources and targets to proarrows and cells. So a generic cell is depicted like this. So for us, proarrows are going in the horizontal direction, arrows are vertical. And then finally, there is externally to these two category structures, functors giving what would be in this orientation convention the horizontal composition and identity. And those obey the category laws up to isomorphism. Okay, so I am going to go into a bit more detail about lax functors because they play a really crucial role here. So I want to try to give you some intuitions and ideas about what these do. So the basic idea that one should have about lax functors between double categories is that there are, well, there's some kind of structure preserving map between double categories, but they preserve the composition strictly in the strict direction of the double categories, so in other words, the vertical direction, and they preserve it laxly, though, in the pseudo or horizontal direction. So to drill down into this, the data of a lax functor between double categories consists, first of all, of two ordinary functors between the underlying categories of objects and arrows and proarrows and cells. And those are compatible with the source and target functors. And then the other data are the laxators and unitors, which we might also call the comparison cells between the composition operations. So for any composable pair of proarrows in the domain, we get this special cell, the laxator, which compares the image of their the composite of their image to the image of their composites. And there's also a unitor cell, which compares the external identity of the image to the image of the external identity. And these are not isos in a lax double functor. And then they obey some axioms. I'm not going to state all the axioms. They are similar to, and in fact actually generalize, the axioms for a lax monodal functor. So these comparisons need to be associative and unital in a certain sense. Then the key thing, though, is that there is a naturality axiom that also constrains how these comparisons behave. And I want to pay a little bit more attention to that because it is sort of, to my mind, the crucial axiom that sort of makes these things behave well and do what we want to in a lot of contexts. So the naturality axiom for laxators is this one. There's an analogous one for unitors. It basically says that if we have two horizontally composable cells in the domain, the image of the composites of those things is not equal to the composite of the images, but they're related via the comparisons like this. So this is a generalization of the axiom that you may have seen for a lax monodal functor. Okay, so yeah. Yeah.
Since you said you wanted to get this pretty well, you're secretly drawing all your cells in the underlying virtual double category?
No, I don't.
Because it looks like FM and is written as binary, right? Like you could write FM circ FN all the way from FX to FZ if you wanted to, couldn't you? Like in the top right cell.
The top. sorry, I don't.
Is it right now with the top?
So so it's true that these pictures make sense actually in any virtual double category.
Yeah.
Yeah, and maybe at the end I can talk a bit more about that, but yeah, we're working. Yeah, lax functors between double categories correspond in a certain sense to functors between virtual double categories. We can maybe talk about that more later. Okay, so sorry to put so much text on this slide, but I want to sort of be able to drill down into what's happening, because we are going to start to see why it is that lax functors seem relevant to doctrines. So we're going to look at what a span-valued lax functor on a strict double category does. And so what we can see is that for every object in my domain double category D, this tuple of data here is precisely the data of a category, because what is it? So we have, first of all, a set f of x of objects. The span given by the image of the external identity pro arrow is the span of morphisms along with their domain and codomain maps. The laxator at those two identities gives a composition operation between morphisms with compatible domain and codomain. And finally, the uniter gives an assignment of identity morphisms. And if you trace through, you can see that the associativity and unitality axioms of the lax functor are precisely the associativity and unitality axioms of this claimed category. And moreover, if we take an arrow in D, the image of this data here gives a functor between the corresponding categories, because the image of the arrow f gives a function, which is a map between objects, and the image of the external identity on that arrow gives a map of spans, which gives the morphism assignment of the functor in a way that's compatible with the object assignments. That's precisely what that's doing. And then finally, the functorality is coming from is a consequence of this naturality axiom. And I guess I maybe could have written it out, but I was running low on space. But this is the axiom that makes that work. And it's a little bit more work to see this, but still pretty much just a direct verification that if we look at cells in D whose domains and codomains are identity pro arrows, then the image of that is precisely a natural transformation between the corresponding functors. So we're already seeing here that lax functors, just what they want to do is they want to send objects to categories, arrows to functors, and a certain kind of cell to natural transformations. So that's encouraging. And of course, we could look at targets for these functors besides span. So we can generalize this in different ways. So we could, first of all, replace set with some other category S that has pullbacks. And we get there's a double category of spans in those. And then you can directly see that lax double functors into spans in some other category S are precisely giving, in the sense of this previous proposition, categories and functors and natural transformations that are now internal to S. So we're getting some of the basic notions of internal category theory. And similarly for enriched category theory, so I won't go through this in complete detail here, but basically if we start out with some distributive monodal category V, where by that I mean we've got coproducts and a symmetric monodal product that distributes over them. We can make this category of V matrices. So the idea here is that the objects and arrows are just sets of functions. The pro arrows are V-valued matrices, as long as we're willing to imagine that the rows and columns of our matrix can be arbitrary sets rather than just a finite number of things. and then cells between V matrices are parameterized families of maps in the base category V. And I really like this double category. The way you compose V matrices is just by the usual sort of matrix multiplication formula, except we interpret the multiplication as tensor, and the addition is coproduct. And if you look at lax double functors into this double category VMAT, then we get categories, functors, and natural transformations in the sense before, but now enriched in V. So we're getting some of the basic notions of enriched category theory. Okay, so we haven't yet talked about what lax functors do to pro-arrows that aren't identities. So they do something good here too. So if we start with an arbitrary pro-arrow in the domain D, then the data that consists of this tuple here is precisely a pro-functor between the corresponding categories. And the way that works is that this pro-arrow M gets sent to the span of heteromorphisms with the source and targets of those, and then the laxators here are giving you the left and right actions of the categories on the heteromorphisms. And then finally, you can check that if you have an arbitrary cell in D of any kind, then its image is a map between profunctors, which is a kind of, again, a kind of natural transformation. And as one would expect, if you replace span with some of these other things, so like spans internal to a category S give you profunctors and maps between those internal to S, and similarly we get profunctors and maps of those that are enriched in V. So this to me is like really kind of amazing. I mean, like, so it basically is saying that already implicit in the notion of a lax double functor are all the most basic definitions of category theory. It knows what categories, functors, and natural transformations are, and it also knows what profunctors and maps of those are. And we'd seen some glimmers earlier of why double categories might be useful as a substrate for understanding doctrines, but I think this is the first like really kind of like compelling piece of evidence that we've seen so far. The fact that it already has all this stuff in it, that's just what it wants to do, is pretty encouraging. Okay, so this is sort of the starting point or the motivation to build a notion of double theory whose models are going to be lax double functors. So now we're going to start to look at some simple double theories and their models. This is the most kind of basic notion of double theory that one could consider, but it's a good place to start for a couple reasons. It already contains like most of the real sort of like ideas behind this stuff, and it also does manage to include some interesting examples as well. So we've just seen in a sense that there are some very simple examples of double theories, because by what we've seen, like the double category that's free on an arrow has as its models functors and stuff like that. But we can build some other things that might look might seem more interesting as examples of doctrines. So two that are included here that are particularly important are there are simple double theories of adjunctions in monads, and we'll see one of those in some detail. Okay, so as I said before, but now to recapitulate, since we've sort of have a bit more of a handle on the details, some of the details, a simple double theory is a small strict double category, and we're now we've motivated why we might want to consider a model with respect to an arbitrary double category, so a model of simple double theory T, and any double category S is just a lax functor from T to S, and we call this receiving double category the semantics. And by default, like if we don't say otherwise, the semantics is going to be span, or if you prefer, it's equivalent to consider just set valued matrices. But as we've seen, there's good reasons to also consider other semantics sometimes. And so as a further bit of analogy to motivate this viewpoint, pre-sheaves and co-pre-sheaves are just ubiquitous structures in pure and applied category theory, right? So much of the work that we've done here at Topos has been around viewing co-pre-sheaves and related structures as databases, and they, of course, they have a ton of important roles in pure mathematics. Models of simple double theories are essentially a lax notion of co-pre-sheave from that perspective. Okay, so let's see a first non-trivial example of a theory. So the theory of monads so we're going to present double theories by generators and relations. At the beginning of the talk, I said that was something that I really wanted to be able to do. It's a nice thing we can do with this. So I'm going to say that the theory of monads is the double category that's generated by one object, an indo arrow on that object, and two cells that are of this shape. And the one on the left is called the multiplication. The one on the right is the unit. And they need to obey three different equations that express some kind of associativity and unitality laws. So I think I've written one of them here. So this is what the associativity axiom looks like. You've probably seen the definition of a monad before. So this is somehow encoding that in a kind of formal way. Using the kind of results that I've gestured at previously, you can see pretty directly that a model of this double theory consists of a category, first of all, along with a monad on that category. And so we can ask about, right, so that's good. But we don't actually, this theory is actually purely two-categorical in a sense. You'll notice that the only pro-arrows that appear are identities, so we didn't actually really need double categories maybe to do that. But we also want to look at the morphisms between models of this theory, and this is where double categories, as I suggested at the beginning of the talk, are going to do more work. So, one of the other objectives of any notion of doctrine, besides giving at least a two-category of models, is to give an account not just of the strict maps between structures, but of the pseudo or lax ones. And that's what we're going to turn to now. We're going to look at a notion of transformation between lax double functors that's lax in a sense. So given two lax double functors with the same domain and codomain, a lax transformation between them consists of the following data. So first of all, we have for every object in the domain double category the component of the transformation at that object, which is just an arrow of this form. And similarly, for every pro-arrow in the domain, we have the component at that pro-arrow, which is compatible with the object components. So those components are cells that look like this. And so far, nothing about laxness here. An ordinary natural transformation between lax functors also has this data. Now the laxity bit is going to come in. So for every arrow in the domain, we have a naturality comparison at that arrow, which is a cell in the codomain of this shape. So rather than asserting that the arrows on the left and the right side of this cell are equal, which is what one would normally do in a natural transformation, we're just going to assert that there's some, not necessarily invertible, comparison between them. And as you might expect, this data needs to satisfy some axioms. I think there are 3 of them, but I'm not going to state them here. But what I do want to point out is how roughly what this is doing with the theory of monads. So if we have a lax transformation between models of the theory of monads, what that unpacks to giving is that, the components of the transformation at the generating object in the identity parameter on that object give you the data of a functor between the two categories that the monads are on. And the naturality comparison at the generating arrow t gives you the data of a natural transformation of this form, and the axioms of the Lax transformation assert that those are compatible in a certain sense with the monad multiplication in units. So this turns out to be precisely the notion of monad functor that appears in Street's formal theory of monads, very influential paper. So that's good. This is some kind of first check of correctness. We're recovering the notion of map that we're supposed to get. And so now okay, so we've seen models of the theory. We've sketched what the morphisms of models look like. Now I'm just going to give you sort of like a little glimpse of the higher dimensional structure here. I'm not going to give basically any definitions at this point. I just want to give you a sense of sort of what's involved. So first of all, for any double categories D and E, there's not just a category, but a two category of lax functors between them. So the objects are lax functors from D to E. The morphisms in this are lax natural transformations, which we've just discussed. And the two cells are a thing called modulations. This is sort of an unusual use of the word modulation. This is a special type of modulation that's implicitly between unit modules, but we can define it without reference to that. And in particular, we get from this that every simple double theory has a two category of models. And so, for example, in the two category of models of the theory of monads, that turns out to be equivalent to the two category of monads that Street considers. So in particular, we recover the right notion of cell. So that's good. But we can go further. So we're doing double categories. So it sure stands to reason that we should get some kind of double categorical structure for the models as well. And there is a way to do this. And so now, if I have two double categories D and E, I can make a virtual double category whose objects and arrows are again lax functors and lax natural transformations. The pro-arrows are now these things called modules, which you should think of as a kind of multi-object analog of a profunctor. And there's a hitch here, though, which is that due to the difficulties associated with composing modules, in general, this double category is only virtual. And so we have to look at multi-cells, and these turn out to be some things called multi-modulations. There is some good news, significant good news. First of all, this double category always has units. This virtual double category always has units, which means it has an underlying two category. And moreover, there's a lot of cases in which it's actually representable as a double category. So you get a bona fide double category out of it. So in particular, when the theory itself is purely two categorical, meaning it has only trivial pro-arrows, then there is a bona fide double category of models. So that includes, for example, the theory of monads, as well as a number of others, some of which we'll see. Great. So we get double categories of models. Okay, so now I've got a little bit of time left, so I'm going to say a bit about Cartesian double theories. So simple double theories are really not that expressive. They don't include most of the things that we would consider to be doctrines, but if we just add finite products, suddenly we can express a lot more stuff. So I'm going to be quite brisk here. There's a high-powered way to define Cartesian double categories, but the down-to-earth one is this. We just say the double category D is Cartesian if both of its underlying categories, D0 and D1, have finite products. And then all the external structure, the source and the target functors, as well as the external composition and the identities, all preserve finite products. So Under additional assumptions, our main examples of semantics are Cartesian. So if we start out with a category S that has all finite limits, then spans in S is a Cartesian double category. If we consider a distributive category V, in other words, a distributive monodal category where the monodal product is the Cartesian product, then VMAT is a Cartesian double category. A lax double functor is Cartesian if its underlying functors between the categories of objects and arrows and of pro-arrows and cells preserve finite products in the ordinary sense. And finally, a lax natural transformation is Cartesian if it is strictly natural with respect to the projection maps. So in other words, instead of having naturality comparisons at each of the projections, we have genuine commutative squares instead. Okay, and then we can say that a Cartesian double category a Cartesian double theory is a small strict double category that's also Cartesian, and similarly for models and morphisms of models. So, there's hopefully a pretty clear analogy here, right? So we started off by thinking about finite product theories or Cartesian categories, which are the categorical logic analog of algebraic theories. And a Cartesian double theory is a categorification of that notion. Okay, so as I was saying, with this boost in expressivity, we can encompass quite a few structures. So an incomplete list of examples includes presheaves and co-presheaves, monodal categories, either strict or weak, braided or symmetric monodal categories, monoidal versions of progesheaves. We can do multi-categories. We can do Cartesian or co-Cartesian categories. We can do various notions of distributive monodal categories. So I'm just going to give, I want to single out a couple examples just to give sort of the flavor of what these presentations look like. We can present all of these theories by generators and relations. So the theory of pseudomonoids is generated by one object, two arrows. So one is a tensor operation and the other is supposed to be the monoidal unit, as well as some cells. So we have associator and unitor cells, which assert that the associativity and unitality equations don't hold on the nose, but there are some comparisons between them. And we also add the horizontal inverses to these cells to ensure that those comparisons are invertible. And then finally, we add two more equations asserting the famous McLean pentagon and triangle identities. I won't write those out. And with those definitions, a model of the theory of pseudomonoids is a weak monodal category, and moreover, it has a bona fide double category of models, and that recovers what you would expect, that there are monodal categories, lax monodal functors, monodal profunctors, and monoidal natural transformations. Here's one of my favorite examples. This is a theory which may be a bit unconventionally called the theory of promonoids. So this theory is generated by one object and two pro-arrows of this form, and subject to some axioms. And the point of these axioms is really just to ensure that this is a theory such that for every number n, there is a unique pro-arrow from x to the n to x. And as a result of constructing the theory in this way, a model of the theory of promonoids is precisely a multi-category. So the set of objects, the object x, generating object x in the theory is sent to the set of objects of the multi-category. And then for each arity, this unique pro-arrow is sent to the innery multimorphisms, and then the laxators and unitors of the Lax-modal functors are what give all the different forms of composition operator that you have in a multi-category. And one interesting thing about this, at first I thought it was a bug, now I think maybe it's a feature. In any case, there's something sort of unusual about lax functors compared to the usual situation, because a model of a finitely presented double theory, this is finitely presented, may actually require giving an infinite amount of data. And that can be a little scary because that's not how things kind of usually work in logic. But so if you're not careful about how you construct your theory, you can end up with your model having to specify a ton of data. But nevertheless, this can be quite useful sometimes as well. OK, so I'm about done, which is good. So what I've tried to explicate is that Cartesian double theories are a framework for categorical doctrines that are based on a double-categorical notion of functorial semantics. In terms of the hierarchies that we saw at the beginning of this talk, most of the things and the so-called monoidal hierarchy of doctrines can be expressed as double theories, not all of them, as well as a number of other things. I will point out that most of what's in the so-called standard hierarchy of doctrines, starting with categories with finite limits, do not appear to be models of Cartesian double theories. They're going to require, presumably, extra double categorical structure to specify. So it's interesting. So I did want to make that clear, though, about like what kinds of structures are accommodated by the theory in its present form. OK, so the paper, which I mentioned at the beginning, covers a whole bunch of additional stuff. It does it in a lot of detail. So one aspect of the story, which I haven't really drawn out too much here, is the role of equipments and the way in which one can actually, at least by restricting to the pseudo maps between models, get equipments or virtual equipments of models. And there's a fair number of other things. I think I will stop there, though. And yeah, happy to take any questions at this point. Thanks. Yep.
Great, thanks, Evan. Are there any questions other than me? I have a question.
Great.
Which one? Do you know whether there's a strictification theorem for pseudo double categories?
For pseudo double categories, there is a strictification theorem.
Must be, but I wasn't aware. So this is.
Yeah. So you can strictify. I believe you can strictify pseudo double categories and pseudo double functors, but that doesn't help you with lax functors.
Sure.
Yeah.
And does anybody know anything? So you described when the double category of lax functors D to E is, when the virtual double category of those is non-virtual in terms of D being degenerate, shouldn't there be some kind of condition in terms of colimits of some kind in E to allow composition of modules? Does that seem
yes.
plausible?
Yeah. So I guess those statements were about reference to models. Okay, you're right. I'm missing some hypothesis there. Thanks for pointing that out. I'll correct these. Yeah, there needs to be a hypothesis about the receiving double category E having local co-equalizers.
Oh, that's true even for the two categorical?
Not for the two categorical.
Yeah.
So this one's fine. This one's fine. Or this last part needs an additional hypothesis that the representable as a double category needs.
It's not one or the other, D being two categorical or E having local co-equalizers?
Well, it's both, right? So there are a couple things going on. So you need E to have local coequalizers to be able to compose like some of the pro-arrows in E that are involved in a module. But there's a further difficulty that even if E is like span, you cannot in general compose modules. So one of Perret's papers, which I cite here, is actually all about this problem of composing modules between lax double functors, and it seems that the complete answer to when you can compose them is not known. So this condition about D being two categorical is a sufficient condition. It's not necessary. But yeah, thanks for the point about the local coequalizers. Yep.
So it seems to me that the like at the beginning you started out with this analogy between like one monads, two monads,
Yeah.
these series.
Yeah.
It seems to me that like the like really it's like one monad, higher monads, and the fact that two monads are historically monads on cat is not necessary. Like it seems to me like right, that's like the two categorical monad story.
Mm-hmm.
But like could you also do like monads, like double monads essentially?
Maybe. I mean, so one of the questions that we haven't addressed at all, which is like a very natural thing to ask given the equivalence between like finitary monads and monads on set, is like how does this story relate to, doctrines as two monads, and can you go in different directions? Yeah, all of those are, as well as your question, are natural questions. I'm not sure. I will just point out that even in the standard work on two monads, people sometimes consider two monads in two categories besides cat for various reasons. Cat's sort of the default choice, but people do look at other ones sometimes.
How does this apply to, how does this apply to the algebraic Julia project?
Yeah, so at some point, I want to implement a version of this story. Whether it's exactly this form of it, I don't know. But one thing that should be the case is that given a double theory of some kind, it should be possible to extract from it a GAT that would have the same models. And that would also automatically give you all like the sort of naturality axioms and stuff that are really easy to forget when you're writing down GATs. So that's one possible application of this stuff, is that it should give you more succinct ways of giving GATs for different kinds of categorical structures. Because if you look in CatLab, you can see that some of those theories are actually like quite enormous, and often we don't bother to write down some of the axioms. So,
What's the title of your paper?
the title of the paper is this one, although it's not yet on the archive. It should be soon. Yep. Thank you.
Great. Let's thank our speaker again.